Okay, so this morning I'll be talking about a developmental validation that we've been doing with the New York State Police, Barry Dusman and company, for 5 years or so. It's a long-standing study. And we'll be describing the basic methods briefly. If you got the materials, and as you can see, I'm not going to spend the usual day and a half on the course that I would go through. I'm going to try to summarize in about half an hour the methods, the validation approach, the results, and how it played out in court, and what the study looked like. Next slide. See, I'm glad you're doing it, because I haven't. So, like Adele and most forensic scientists or scientists these days who work in comparing hypotheses, we use likelihood ratios. And I'll, oops, can I just move that out of the way? Sorry. If I fall through the screen, that wouldn't be helpful. Well, I'll tell you about that later. So the identification, in this talk, I will be using no math, except maybe for a probability here or there. Okay, this is very difficult for me, but I'll be using no math. The identification hypothesis is, it used to, 20 years ago, people would say the person's guilty. Nowadays, it's more diplomatic to say an individual or reference contributed to the evidence. And that's the hypothesis that we have. And our question is, what's the data telling us about the hypothesis? Well, we care about the information gain. Before we look at the data, we have our belief about the hypothesis, based on whatever evidence, general knowledge we have, and so on. If you're a trier of fact, you may have it. If you're a scientist, you have your odds. And what the odds mean is that it's the probability of the hypothesis divided by the probability of the alternative. Did it, didn't do it. Contributed, didn't contribute it. What's the ratio of those two probabilities? You have your odds, and then, whatever they are, you look at the data, and you go from before to after. And you move from your prior odds, what you had before, to what statisticians call the posterior odds afterwards. What are the odds of the suspect contributed, the hypothesis, after you've looked at, in this case, the DNA data? Okay? And then there's a change. Maybe it's the wrong person, and your belief has gone down tremendously by 20 orders of magnitude, or maybe it's gone up. And that ratio of the change of information, the change of your belief, based on the data, is independent of whatever your initial belief was. That's the beauty of likelihood ratios. No matter what you thought, the data will give you the same gain regardless of where you started. And so that information gain, as originally defined by Jack Good in 1950, is the likelihood ratio. There are many ways of computing likelihood ratios. Adele showed one of them. That's pretty popular in forensics. But there are about 20 ways of computing likelihood ratios. They're all mathematically equivalent. And this is the definition. What did we learn from the data? That's objective, and that's what's presented in court. Okay, and as Adele was doing as well, sometimes when you talk about numbers like a trillion, it's easier to talk about 10 to the 12th and use the log, the order of magnitude, the powers of 10. 12. So if you hear me saying 12, I'll usually mean 10 to the 12th, because those are units we can add together. If each locus gives you maybe 1 unit, you add together 13 loci, you get 10 to the 13th. 1 plus 1 plus 1, 10 to the, and so on. Okay? Next slide, please. What is a mixture? That's what the study's looking at. It's good to define. So we have maybe contributor A, contributor B, and we want to, in nature, these different DNA contributors have been added together. In blue, I'm representing 2 alleles from contributor A, and in orange, smaller amount, they have lower height, lower amount, right, of contributor B. We add them together. Actually, we don't. Nature adds them together. This is evidence. And after we do an amplification on them, we get data that indicates that there's more of one than of the other. In general, with some random variation, computers model that. So this is what mixture data looks like. You see it's a quantitative pattern. Within random variation, if you had a lot more of A coming in than B, generally you have taller allele peaks for A, than for B. Okay, so that's mixture data. I'll be using that cartoon as we go. Thank you. What is mixture interpretation? Well, mixture interpretation is the same, whether a person's doing it, a machine's doing it, a computer's doing it, using felt tip pens, doesn't make any difference. Everybody does exactly the same thing. There's only one difference in the rules, and I'll describe what they are. The first thing you do is you objectively infer a genotype. Don't look at the suspect. How do you objectively infer a genotype? There's only one way of doing that's valid, using Bayes' theorem. That's the only way of doing it that you can defend, and that is you consider every possible allele pair. You have to consider everything. And then you compare the allele pair, the patterns that are produced from those alleles pairs against the data, and you apply a rule to ask how likely each of those comparisons are. Then after you've considered everything, you divide by the total, use Bayes' theorem, and you get your probability of belief in each allele pair. If the data are single source and obvious and completely clear, you put probability of 1 on one of the 100 allele pair possibilities, and 0 to everything else. Otherwise, like in a mixture, those probabilities are not 1. They're between 0 and 1. You're representing your uncertainty with probability, which again has been the standard in science for 100 years. That's what you use to represent uncertainty, is probability. And after you infer a genotype objectively, whether you're a person or a computer, you then make a comparison with a suspect or a database of suspects, like CODIS, never having seen it before. That's mixture interpretation. And in a few moments, I'll also describe a human review approach for comparison, so you'll see the same steps. So what's the only difference? In overview, obviously there are thousands of details we could go into. I'm not going to be giving you detailed mathematical models of stutter, degraded DNA, relevant application. You can ask me about it, but I'm not going to put that on slides. The difference is the rule, the likelihood function, when you make the comparison. The quantitative rule, which is universal in quantitative science, is instead of writing down equations, which George and Ranajit might like, but other people might not appreciate to the same extent, I'm just going to summarize it in 4 beats as better fits, more likely it. That's the math. You can write down a lot of equations for it, but that's all it's saying. What it says is if I have 2 big peaks, 2 little peaks, I'm trying out all possibilities, putting alleles all over the place, different heights, different amounts, different uncertainties, that if that's the data, too high, too low, and I get a wonderful fit, that has a high likelihood. Better fits, more likely it. If, on the other hand, I have 4 peaks, too high, too low, and I try to fit, I say, well, no, that allele occurred twice because the blue contributor has those 2, the orange contributor has a new one, but one of the old ones, and I don't account for the 4th allele peak, and I don't really fully explain how tall that peak is, that fit's not as good. And because quantitatively you see that it's not accurate. So if you use your hands, if you want to show this to your kids, if this is the data, right? This is a pattern that's predicted and it fits very well, has a high likelihood. If it doesn't fit at all, 0. Basically probably 0 in the end, mathematically. If it's sort of in between, well, it's sort of in between. And so this might have a lower likelihood. After you've considered every possibility, use Bayes' theorem, you combine the stuff together. I've left out the other 100 things on this list because the probabilities are too low. And some have higher probability, some have lower. That's quantitative inference. That's the first step. That's how you infer a genotype. Then now you have to make a comparison. How do you make a comparison? One of the 20 ways of writing down the likelihood ratio formula, which is easiest to explain to juries and to lay people, but it's mathematically equivalent, when there's a definite suspect that you're comparing to, is at that locus you look at the suspect's allele pair, and you say, at that allele pair, what was my belief in before I ever looked at the data of what that allele pair would be? Well, if you're a geneticist or a forensic scientist, it's the general population. You haven't done any experiments beyond your allele counts. So what's the rarity? What's the probability of seeing that particular allele pair in the population? That's my prior belief, before I saw the data. Now I've analyzed the STR data, say on a computer, considering thousands of variables, let it run for an hour, or by eye. And now you have the probability of that allele pair after you've seen the data. That ratio is one of the 20 ways of writing down the information gain, the likelihood ratio of what you learned by looking at the data. And you'll see some pictures of this later on. It's actually quite easy to explain. I started off with a population probability, maybe 5%. I looked at the data. Now I believe 50%. I have an information gain of 50 divided by 5, 10. That's my likelihood ratio at that locus. Log of 1. Okay? Make sense? Just nod your heads just occasionally. Be good. I know it's a long morning. Now, the other point here is the computer, by its audit trail and its methods, guarantees you objectivity. Because when it infers the evidence from the data, whether it's looking for 1 contributor or 6 contributors, it has never seen a suspect. It wasn't programmed in. Those of you who are old enough to remember Roger Rabbit, remember that fan? See the laughter, we can tell the ages of over and under 50. Jessica Rabbit has this fantastic line, "I'm not bad, I'm just drawn that way," if you remember. The computer has to be objective. It can't ever look at the suspect because it's programmed that way. There's nothing else it can do. That's just the way it is. So first it infers, and then it compares. All right. So, not yet. Thanks, though. And so now we want to look at a validation study. And the basis of our validation study is going to be this universal metric in science and law and forensic science of the information gained. That's what law enforcement needs to know if you're police. That's what a prosecutor wants to know. That's what a defense attorney wants to know. What did you learn from looking at the data? If your likelihood ratio is 20, you're on the right track. 10 to the 20th. If it's 10 to the negative 20th, try somebody else. Okay? At least that's what the data is telling you. Maybe it's not the right data, but that's all the data can tell you. So now let's use likelihood ratio as a single number, or as statisticians prefer, the log of the likelihood ratio. The order of magnitude is 6, 9, 12 for a million, billion, trillion, to look at some cases. So in this study, as Jamie Belrose will tell you about, we looked at 41 cases with hundreds of samples, and from all of those, as you can read in the encyclopedia that we distributed to you, of those meeting the criteria of being clear two-person mixtures, there were about 88 samples within 5 to 95% mixed proportions, and of those meeting those guidelines where there was a human review that we could make a comparison to, we had 16 cases. And you'll see why at the end. 8 happened to have not a victim known. 8 happened to have a victim known. And that's the data I'm going to show you next. Thank you, George. So what you're looking at are 8 cases, and here's the information, the log of the likelihood ratio. So here it's 10 to the 5th, 10 to the 10th, 10 to the 15th, and so on. And you see a range, but this is computer review, 2 unknown, not having, inferring. So what does the computer do? You put the data in, you tell it, please look for 2 unknown contributors. In all of these cases, we're just giving it 1 data sample. Using the laws of independence and statistics, of course, you can put more than 1 sample in with a product of likelihood ratios, likelihood functions. I'm not going to talk about that today, but you can. But we try to make this as straightforward as possible. And then the computer plays with it for, cycles through all the variables, does hierarchical Bayesian Markov check, whatever it does, it's described in the papers that you have. And then after an hour or so, it uploads its answer of a genotype. And then afterwards, it makes a comparison on the database of whatever suspects or population of suspects you asked to make a comparison with. And what you end up with, if as one number amongst many, is the information. So here are the 8 information scores, and the average is 10 to the 13th, roughly 10 trillion. Okay, that's good, but people, as Jack asked Adele a few minutes ago, how about a comparison? Isn't that helpful in understanding? One of our goals in the study was to ensure that the computer was always as good as a person. And if it was to any extent better, by how much? So we can quantify that using log likelihood ratio. And we will. Next slide. What's human review? Qualitative manual review is identical in every aspect, maybe not in protocol details, but every principle to computer review. It has to be, because it's valid. It's a valid way to proceed. The only difference, you try out every possibility, you make all the comparisons, is in the comparison rule. How do you compare the hypothesized pattern of every pattern you're considering against the data? Instead of doing it quantitatively, the rule is now qualitative. It uses an all or none logic instead of a number logic. It's the only difference. And so what happens here, if this is the data with too high and too low, the new rule is, for the likelihood, not better fits more likely it. The new rule is every pair gets equal share, which again is more memorable than writing out the math, unless you're a mathematician. But by a quick show of hands, I'll stick with it. Every pair gets equal share. So if there are 4 possible alleles, and and you have a pair of alleles that are included in those 4, it gets the same value. And if it's not included, it gets a value of 0. So the other 100 things that aren't here might have an allele that's outside of those 4. They get no likelihood at all. And what you see is that any of the 10 possibilities here, all on one or any pair, get the same amount. So whereas quantitatively this may not be as good, qualitatively it's included, so it gets equal weighting. That's the rule. That's what inclusion does. That's the mathematics behind it. All the listed allele pairs are assigned the same likelihood. And what's the result when you match? Well, if you have a good quantitative method, that would be on average giving higher probabilities to things that fit better, because you're being very fair, very socialistic, each according to his abilities, each according to his... They each get their same amount. In general, you get a lower probability, giving you lower information gain, because you're now comparing what you started with, the population probability, maybe 5%, instead of going up to 50% to get 50 over 5, which is a gain of 10. Maybe, I'm not going to put in all the priors and numbers because that's hard to explain, but if you had 10 equal possibilities, each would get maybe a 10%, hypothetically. Going from 5% to 10%, 10 over 5 is 2. So you get an information gain of 2. You still get an information gain. There's information there, but you get less. That's what happens, and you can measure it with a likelihood ratio, the information gain. Next slide. So what happened? In blue, again, on these 8 cases, you see the information from the computer. But now in orange, these are the reported match scores from the case folders. This is what you're seeing. These are obviously not the case identifiers. Everything's been anonymized and so on. Okay? Just in case you had any concerns. And so in orange, you see that we confirmed our belief that in every case, the computer got the same or more information. The blue bar is taller than the orange bar. And now we can also look at the average difference. Human review, if you do a lot of inclusion methods, CPI, you know is about 1 million, 10 million. That's what you tend to get. And that's what we got, 10 to the 7th, which is 10 million. That's what New York State got. The computer said to New York State, basically, you're right. You're doing a great job. Human review is always is fantastic here. If you reported a score, the computer agrees. That's what it is. It just gives you more information, which you could use or not use. The average information gain, the difference between the averages, is 10 to the 6th, or about 1 million. So you get about 1 million-fold information gain when you don't have a victim and you're comparing a 2 unknown problem by computer with CPI. Next slide, please. How reproducible is it? Well, these are statistical search programs. You have a Bayesian model, and you put in the data and you run it for an hour or two. It samples, it looks through thousands of variables, tens of thousands of times each cycle, and when it's all done, it has a genotype. And then you can say what's the likelihood ratio. So if the answers were always identically equal, either you're looking at a trivial problem like a single source, or you're using Photoshop to create your slides. In the real world, you need some variation. That's what you get with statistical sampling. What is the variation? Well, in a 2 unknown case, as described in what you have, you can compute a within-group standard deviation. Formula's there, number 2 if you want to look at it and think about it. Whatever. Statisticians have known this forever. But you can think of it as if I look at the difference between the replications, what's that average difference? You can also do this with 3 reps, 4 reps, and so on. It's a way of, when you do a validation study, you want to assess efficacy and reproducibility. The last slide was efficacy, gain of about 1 million. This is reproducibility. The standard deviation is a few tenths of a log likelihood ratio unit, an information unit. If you think about the current population databases used giving you about a 1 likelihood, 1 log LR unit, it's reproducible within what we currently measure and what we do. Next slide. Oh, sorry?
Just on that, I would have expected if they were replicates that sometimes the second one...
Oh, I ordered them for display purposes. Okay. In fact, let me go further. Go back a slide. This is in the legends of the paper. You don't have to go back, but everything, I'll say it on the next round. But no, they're ordered because it's easier to see and it's described.
Okay, I just not having the same color.
No, that's random. Yeah, you're correct. Next slide. Okay, what if you have a victim? When would you have a victim? Well, in sexual assaults, homicides, you have a victim, and you can take the profile, and many laboratories compute, instead of a CPI, a CLR. CODIS PopStats will do that for you. And so now, for the computer's perspective, you give it the same data, you just ask a different question. In fact, with a computer, you can ask it as many questions as you want simultaneously. It goes off and solves them in parallel. You can say, use the victim, don't use the victim, look for 3 unknowns, look for 2 unknowns, whatever. And then you can look at all the results. You can also ask it from the very beginning to do everything in duplicate if you're doing a study like this. Or even if you want to go to court, we like doing everything in duplicate. We like knowing what we have. So we can say it's reproducible. It's a computer. You don't need a person sitting there looking through it all over again. You can run it. It's a computer. So on each case, on an information scale, you get this information, which is an average of 10 to the 17th, not quite a quintillion, but good enough for government work. Next slide. Making a comparison with the CLR statistic that was reported relative to the most conservative ethnic population, because that's how we did this. And this is what I'll tell you. So here we sorted, and it's described in the figures of the paper, from greatest to smallest. So if you like looking for the pattern, you can see that visually. We do it it just helps to see data sorting. The average information gain here is 10 to the 4.5, which is about 50,000. So there's an improvement of about 50,000-fold. And the computer is never giving an answer that's down there, -20. It's never even giving an answer over here, indeterminate. It's agreeing with, confirming, and giving more support to the human review. In this case, by a factor of 4.5 log units, about 50,000. Next slide. The reproducibility, well, here you're looking for 1 unknown, not 2 unknown. It's an easier problem. In fact, from the computer's perspective, it's looking for 1 unknown, and it's solving the mixture weight problem at every locus and for the templates that are involved. So it's not much harder, really, than a 1 unknown problem for the computer. And when you get down to a 5% mixture, maybe. And so the reproducibility is now measured in hundredths instead of tenths when you look at the standard deviation of the within group standard deviation between the 2 computer runs. Okay? So for efficacy and reproducibility, we basically see on this data set it's efficacious and it's reproducible, which is the whole point of a quantitative validation study based on statistics. Next slide. Let me sum up that comparison. Jack, I'm going to go just a little bit over, but not too much. Okay, thanks. So let's look at the 2 unknown and the 1 unknown, summarize it, discuss it, and then pretty much move on. With the 2 unknown, without the victim, we saw that the quantitative computer had a max score on average about 10 trillion, log units 13, with tenths of a information unit reproducibility. Human qualitative review using everything the same except every pair has equal share as opposed to better fits more likely it. The only conceptual difference in principle, qualitative versus quantitative, of 10 million on average, and that information gain averaged about 1 million per case. Okay, 10 to the 6th. What about when you had the victim, and that's available to you? Well, there you've got a bit more information. It's about 100 quadrillion, 10 to the 17th. Human review gets more information. It's about 50 trillion, 10 to the 12th. And again, you get an information gain of computer versus human, of quantitative versus qualitative. The reason I say computer is that it's really hard for a person to look at 1,000 variables, do the calculations, and then repeat this 10,000 times. I mean, somebody might object. But the computers don't object. You just feed them electricity and some cooling, and they just keep going. Okay? Talk to them every now and then over a network, keep them happy. And that information gain was 10 to the 4.5 or 50,000. Now what's interesting, and we're going to see this in the case in 2 or 3 minutes, is the comparison of if you had a choice. Suppose, hypothetically, you have a homicide and you have a victim, and you're looking for one unknown. Some groups might choose to do an inclusion method. Other people might not. And you can compare with the computer. That comparison, which really is often what happens in practice when laboratories prefer to do inclusion, because, as Adele said, it's easier to explain in court, and there are some things that are nice about it. That information gain is 17 minus 7, or 10 to the 10th. So it's about a 10 billion-fold on the sample set information gain. So one would expect that a computer using the victim looking for one unknown on average, would do considerably better than inclusion. That's simply what the data show. Next slide. In summary, for the validation component, before we move on for the direct comparison, information gain, or likelihood ratio, is a universal measure for looking at what you got from a DNA interpretation. Now, to do it, yes, so think of it like this. I infer what I infer by many different methods, and then after I'm done, I have a fixed suspect or reference profile and a fixed population. Relative to those two being fixed, all of those comparisons are comparable of what you inferred, because each one will give you a number with respect to the same suspect and the same population. For efficacy, we see the computer does extract useful information. And there is some improvement, fortunately. I mean, it's fortunately that it extracts the same, but it's nice that it improves. It turns out to be as or more informative than human review. When there is a victim reference available, it's about 50,000-fold. Without a victim, about 1 million-fold. It's reproducible within tenths or 100ths of a log unit, depending on what your question is. It's objective. I don't even need a show of hands. Some of you have heard about the sequential unmasking stuff. We heard it again last week at AFS. They have a new website, the books, the T-shirts are coming out soon, whatever it is. And so the issue with that is that it makes this presumption, I think it's really a problem, it makes this presumption that, forensic analysts are not objective, which isn't true, because that's just not what happens. But all this goes away. It's all nonsense with a computer. Because in parallel, you ask 50 questions of a case. You can't see the suspect. The computer doesn't know how to. It doesn't even know what the question means. Tell me, find something and I told you what to look for? I mean, it can't do it. It has to try everything, because that's what it's programmed to do, like Jessica Rabbit, right? It has no choice. It just has to do it. So in parallel, it finds everything, whatever it is, and afterwards it makes a comparison. It's guaranteed objective, which can be helpful if somebody's questioning you about that. It has no choice but to be objective. For productivity, we're going to go into this at the very end, but we'll see that the computer basically always gives a statistic, which is almost always usable. And laboratories, we'll see later on, I'll show you the data for that, give you an answer maybe 1 out of 3 times. And that has some implications, which we'll talk about. And this sort of science is useful whether you're doing scientific studies of the type that Adele or we or Barry and other groups do. It's useful for investigative purposes to try to find someone. It's also good as evidence when you're trying to implicate or exculpate. Next slide. Steve.
Mark, what would happen with your...
Why don't you back up one?
What would happen with your improvements, just ballpark? if the only data that you loaded was data from validated existing forensic thresholds, whether they be detection or stochastic. So we've got SWGDAN doing what they're doing. And my question to you is, if we forced you, I know that you wouldn't want to do this for reasons that we've talked about in different locations.
Mainly having to do with public safety, but yes.
Well, I think it's an important issue. I don't want to hijack the conversation at all, but what happens if you use the existing thresholds or the ones that are being proposed to the number and the improvement?
Let me give you the answer. So, two answers to that. Should you choose to be more conservative in your human review, you would see an improved, the computer result would not change because the computer models probability distributions of peak heights, as some of you know because you've heard talks on that, and makes no use of such thresholds. So the computer improvement would get greater. But interestingly, in the standards that came out of the SWGDAN Mixtures Committee, importantly, they put in a paragraph that said if you're using probability computer modeling methods that do not involve stochastic thresholds because they're accounting for it in a different scientific way, then you need to conduct validation studies, as we have done, and then that's perfectly legitimate. So the practical answer is that compared to where human review with stochastic thresholds is going, the computer will be getting an even more apparent information gain. Philosophically, all that's happening is that the data contain identification information. If you use the best possible likelihood function, which is a better fits more likely it, which other groups I'll talk about this in 5 minutes, many groups are using for research papers, science, and so on, then the goal of that is to extract objectively everything that's there. If you put other criteria on, certain thresholds, restrictions on thresholds, other ways of doing qualitative review with a less informative likelihood function, then you're artificially reducing the identification information that is present in the data. Is that a good answer?
It's one way of describing it.
Well, that's how a statistician would describe it. Okay. So I don't want to repeat it, but the data has information in it. And if you do the sort of science that you'll find in thousands or tens of thousands of articles in the scientific literature now, in Science, Nature, Journal of American Statistical Association, the standard scientific literature outside of forensics, the standard approach is to ask the question, how much information can I get from my drug study? How much information can I get from my gene chip? How can I maximize the return on investment as measured by information? That's all the computer is doing. And that's what I'm describing. And some of the details are in the papers that you have, which I've gently put into the appendices. So those of you who don't like looking at statistical modeling, some of you do, some of you don't have to read the appendices. Okay? Next slide. Can I go on, or do you want?
No, go ahead.
Okay. How does this play out in court? Let me tell you about a case that I testified in last year. This is State of Commonwealth of Pennsylvania versus Kevin Foley. In 2006, Blairsville dentist John Jelinek bled out in his home after being slashed by some unknown assailant. And Pennsylvania State Trooper Kevin Foley he was a University of Pittsburgh football fan, was charged with the crime. Kevin Foley happened to be the, get this right, the boyfriend of the estranged wife, who, it's a very interesting, complex story. You can read about it. Anyway, he was charged with a crime, and because it was a Pennsylvania trooper out of Greensburg, the analysis was done by the Quantico Lab, the FBI in Virginia, and when they came back with their inclusion statistic of 13,000, it was in the papers. I mean, Blairsville's an hour and a half east of Pittsburgh. It made it in the Pittsburgh papers. Why is it if the population of Pennsylvania is 13 million, who cares about a statistic of 13,000? And the only physical evidence, next slide, that was really linking the defendant, or the suspect, the defendant at that point, to the crime was DNA. Here's the DNA. The DNA was extracted from under the fingernails of the victim. He evidently had reached out and scratched somebody, And you mentioned circumstantially that the trooper did have a scratch over his eyebrow the next morning, but that's just circumstantial. There are two contributors to the DNA. I'll show you some data. One with 93.3%. The victim's DNA alleles are just towering over anything else that's going on. And they're sort of at the bottom is 6.7% of some unknown second contributor. There was adequate DNA, about a nanogram of DNA, 1,000 picograms. STR analysis was done by the FBI lab with Profiler Plus and Cofiler. We know the victim's contributor genotype. We have it, and we see him in the data. We were asked by the prosecutor to do true allele computer interpretation using quantitative methods, looking at the peak heights. And from that, we inferred the unknown contributor genotype, which, as you've just heard, just like inclusion, is a probability distribution. It just places different weights on what it sees based on the evidence using its own likelihood function. Only after having inferred the unknown was any comparison made with the suspect genotype. Next slide. 3 match statistics were inferred. The inclusion method gave a score of 13,000. Dr. Robin Cotton was brought in, kind of like as an arbiter, because we had 2 scores, to give a score using an obligate allele method, which I'll refer to as subtraction. It gave a score of 23 million. And the computer, TrueAllele, gave us a score of 189 billion. And so the first questions that you can ask is, why am I looking at 3 different match scores? In fact, you can even ask more fundamentally, what the heck is DNA interpretation if you get scores ranging from thousands to billions? What's going on? How do these interpretations methods differ? And what should we present in court? So let me answer that. So what's the difference? Well, the only real difference between inclusion, obligate allele, and quantitative review is the data that's used. And this is something we showed to the jury. It's one of these things where I came in with 50 slides. I felt like an Alice's Restaurant with all the circles and arrows in the back of every color glossy photograph, and he chose 4 pictures. So this is one of the 4 things that got shown, because it made a lot of sense to the jury. There's a victim profile, there's quantitative data. Inclusion does not use the victim profile, nor does it use the quantitative data. It uses an all or none method. Every pair has equal share. The obligate allele method does use the victim profile, but does not use quantitative data, and a quantitative method, in this case, used both. Next. So there was a Frye hearing, as you might imagine, since this, as far as I know, was the first time somebody was presenting this sort of quantitative computer modeling result. And we went through, and I asked Kathy, just so you could see what we did. We've updated it since then. But this is what we actually showed at the Frye hearing. About 50 references. I'm not going to, if you ask, I'll go through whatever you want. It can take hours. And you'll miss your flights and you'll blame me. And we also gave them a CD that had every article on it, so they could go off and Larry Moeller could mull over whatever he saw and enjoy it and have fun. So in overview, what we saw was there's a long literature on quantitative STR peak information and how it's used. People have known in many fields that it's roughly linear, proportional. The more that comes in, the more that comes out in proportion. Genotype probability distributions have been around a long time. I think Mendel wrote the first paper on it back in the last century. Yeah, we can discuss it afterwards, but I didn't put it in. Yes. But a Punnett square is implicitly giving a probability distribution of a genotype. That's what it is. Okay. Computers have been interpreting STR data almost from the very beginning. We give a bunch of articles both for how that's done. For statistical modeling and computation, this is a fascinating story that I won't go into. I guess it started during the Baum project and has a fantastic history. You can read about it or you can ask me about it afterwards. I won't tell you about it. But basically, in the last 20 years, the concept that you can build hierarchical models, not just work with bell curves and large numbers, but build models with thousands of variables and use them to solve problems using statistical search, Markov chain Monte Carlo methods, has become the norm in science. You can solve very complicated problems by modeling them and computing them in ways that people were not doing 20, 30 years ago. They are now. It's the standard. There's a large likelihood ratio literature starting off in the 1950s with Jack Good's book, Savage's book, and it's building on that of the notion of how you would compare two hypotheses in a way that expresses the sensitivity and specificity in one number and can be combined by independent experiments either simultaneously or sequentially. Mixture interpretation, there was an interesting ruling 2 years ago now in D.C., the Roberts case, which indicated, and the judge found this helpful as well, that while the data can be debated, mixture interpretation in that court's view was always admissible because the expert could be brought in subjected to cross-examination, and the defense could bring their own experts in. So in some sense, in theory, you don't even need to do a validation study. We're not such cowboys. We like validation. Then there are a number of systems for quantitative DNA mixture deconvolution. The most interesting one at trial, or the hearing actually, was Jim Curran's paper from New Zealand, where he actually wrote a program and published with very similar mathematics how to do two-person mixture methods, inferring genotype probability distributions, using hierarchical Bayesian modeling of mixture weight and genotypes, using Markov chain Monte Carlo. That was very impressive. It was just published, and that's what maybe 3 or 4 groups around the world do research on. It gives, as he found, got a lot more information. You'll find a description of how much more information in the match likelihood ratio paper that I gave you, where I described not our results, but Jim Curran's results, and how you can understand what he did. And then we showed our own publications. And the judge found that helpful in his report, and we went on to trial. Next slide. Something else, though. Okay, I'll go faster. No, I'm almost done. You have this paper. This is the DNA information gap paper. What this slide says is that on a controlled laboratory study of mixtures and dilutions, each point represents one experiment where we happen to know the amount of DNA, and we measure, after we infer the genotype, how much information we got. Here's a scatter plot. What do we see? We see exactly what you would expect. Human review goes down to about 100 picograms of DNA on a large log scale, and then people aren't comfortable below that. The computer continues down to about 15 picograms. It doesn't have much of an issue with that. And then we could use this study, which is published in PLOS ONE, as a calibration curve and say with a 6.7% mixture of 1,000 picograms, how much information would we expect? Well, for 15 loci used, a quadrillion to 1. With 12 loci, a trillion to 1. That's what we saw. So the defense's contention that we should have seen what the FBI saw simply wasn't supported by the data. Next slide. And basically, I testified the usual thing, like in the European report about mixtures, that we just used more of the data. Adele said the same thing. The best metaphor was the notion of a magnifying glass and a microscope. The naked eye was one method, magnifying glass the next. The microscope was the most powerful. Same data, same slide, but better resolving instruments on the same data. Next slide. I told a whole story about pneumonia, but I won't go into it. Let's use that microscope for 3 minutes and just see what stuff looks like. These are all shots from Trulio. And we present everything visually so people can understand it. 3 years ago, it was all numbers. We didn't even know what was going on. Now it's all pictures and numbers. This is the mixture distribution on a scale of 0 to 100%. We see it's 6.7% with some probability distribution. Next slide. This is what, as you have read about, what a DNA profile looks like. At every locus, there's a probability distribution. Out of the hundreds of possibilities, sometimes there's one possibility. Other times there might be 2 or 3 or 4, and they have some probability associated with them. You can show the same picture with CPI, and you see a lot of things that are lower and more equal. Next slide. This is what the log likelihood ratio looks like. This is 10, this is 100 on a log scale at every locus. If it were a mismatch, you'd see everything in red pointing to the left with a number of around -20 sitting there. Next slide. This is what data look like. Here we see the victim, 12, 14, some low-level peaks. The 15 is not in a stutter position, so it's probably going to be there. Next slide. And this is an explain interface where you can do a what-if analysis quantitatively as a user to ask why the computer did what it did. In the case that will end up matching of 12, 15, the blue is the 6% of the unknown. That's the victim. And when it generates the pattern accounting for stutter, pref amp, and everything else, you see that the pattern in gray matches the data in green. Now, it's not the only thing that matches. If you were to put both bets as a 15-15 homozygote, you get some comparison, but almost nothing else really works very well. Next slide. As we see, when we go to the report interface, and in dark blue, quantitatively, that 12-15 shows that a better fit's more likely it. 90% of the likelihood goes there, a little bit to the homozygote. Human review, with inclusion, though, places its bets equally across all 6 allele pairs for those 3 alleles, including the 3 where there's not even what would be an obligate allele of 15. So this is, again, the only, we can run anything through the system, including human review, for comparison. This is the only difference. Quantitative, qualitative. Better fit, equal share. Next slide. This is what a report looks like. We hand these out as well. We have a short form and a long form. The short form is a trial. This is we can put in co-ancestry if people like that. It's very popular overseas for mixtures. This is the D8 that we'd looked at. This is how you do a likelihood ratio. At 12-15, it gave it 90% probability. What you believed before was 3.6%, the population. The ratio of those two is 25, 90 divided by 3.6, and the log of that, base 10, is roughly 1.4. Add them all up, take 10 to the power, and you get 100 billion. And this is quite easy to explain. Well, next slide. We showed this at trial. The prosecutor wanted to show that it wasn't magic. He was very comfortable showing multiple results from different experts. Each expert explained how they did it, and it was explained why the methods were different. So in orange, actually, what do we do? Inclusion is purple. You see, you get a little bit of information here. Of 10 to the 4th. When Robin Cotton did an obligate allele method, her 4 allele cases where a unique result is pulled out as the minor contributor at 2 loci, D7 and Tho1, gave a tremendous amount of information. And it went up 3 orders of magnitude to 10 to the 7th. Quantitative review with true allele got those, and as we saw with D8, added a little bit more by more quantitative considerations. And so actually by showing the progression, then for another 4 orders of magnitude of 10 to the 11th of 100 billion, it was clear to the jury that it was really, this wasn't magic. There was a progression. If you used more of the data, you got more information. Next slide. Okay, so what did we learn from the case? It was an objective review. I'll be done in 5 minutes. Shoot me in 5 minutes.
You said 2 minutes last time.
Yeah, but that was an estimate. That was manual. This is by computer.
We're going to get moving.
Okay, yes. It was objective review that never saw the suspect. We found it straightforward to testify in court. It was understandable to the triers of fact. Before it didn't, but now it has precedent. It's been admitted, testified to, accepted, and so on. The key idea was to preserve match information that's present in the data. That's been the theme of our research for the last 20 years and the papers that we write and what we do. The attorney liked the fact that we got the data on a Friday and he got his answer back on a Monday, which computers can do, despite how complex the case was. And the main lesson we learned was that it was quite easy to present multiple match scores in court and explain them, different experts. And Nothing was withheld from the jury, and this is part of the way forward with New York State, as we do parallel work, continuing with the old method and then adding the new method, and just being able to explain why a closer look gives you more information. Next slide. Kevin Foley was convicted. You can read about it. You have this in your binder. This is about the only readable thing in the binder that has no math in it, which describes the case. Some of you have read it. It has no math in it, and basically it all hung on the DNA. Next slide. This is what you see. This is a 3 unknown case, which you have in your binder, which was resolved into 3 genotypes. Next slide. This is what the genotypes look like. The 60% genotype gave 10 to the 17th. The 25 gave 10 to the 11th. And the 15% gave 10 to the 11th. You see that as there's less DNA, you go from more certainty at each locus to a more diffuse probability distribution. Okay, next slide. Overall, over the 88 cases in duplicate, we see that the median efficacy is about 10 to the 15th, with about 3 cases that were under 10 to the 5th. Next slide. And this is the last slide. So I actually was wrong again. I did it in 2 minutes, not in 5. Productivity. What do we observe in the end? Well, this is the case classification Jamie will go into. For the 35 simple cases, the average was 10 to the 16th, with a standard deviation of 0.1 information unit. And of those, human review could produce a max score in half the cases, and couldn't in the other half. For the 20 intermediate cases, the score went down a little to 10 to the 13th, 10 trillion, increase in the standard deviation, and human review could assign a max score to 25%, 1/4 of the cases, and couldn't in 3/4. And then for the complex cases that made up over 1/3 of the study, which Jamie will tell you about, the average result was about 1 trillion, with a half log unit standard deviation, and of those, human review could produce a max score in 1/5 the cases and couldn't in 4/5. Overall, human review could produce a max score in 1 out of 3 cases, which in lab protocols and good labs mean you keep going. So on average, if you have mixtures and low-level interesting evidence, you have to do 3 tries with 3 reviews, and it takes a lot of effort, time, reagents, and people resources to look at 3 items to get 1 reportable score of about 1,000,000 to 1. The computer on the first try, over 96% of the time, is giving a result on average of over 1 trillion to 1, which is reducing the time it takes in a very objective process with fewer reagents, fewer resources, and so on, which might enable labs to do a lot more with less. Can I stop there, Jack? Is that okay?
Okay,
Okay, thank you.